Johannes Kepler, one of the foremost figures in the scientific revolution, was a visionary astronomer, mathematician, and natural philosopher whose contributions fundamentally reshaped our understanding of the cosmos. Born in 1571 in the small town of Wilderstadt, in what is now southwestern Germany, Kepler's name is indelibly associated with the three laws of planetary motion that bear his name. These laws not only laid the foundation for Isaac Newton's theory of gravitation, but also played a pivotal role in the development of modern astronomy. Kepler's life, marked by intellectual brilliance, personal struggle, and scientific triumph, exemplifies the intersection of genius and perseverance in the pursuit of truth. Kepler's work emerged during a time when humanity's understanding of the universe was on the brink of a profound transformation. The Renaissance had brought with it a renewed interest in scientific inquiry and a challenge to the long-standing geocentric model of the cosmos, which placed the Earth at the center of the universe. The Copernican heliocentric theory, which proposed that the Sun, not the Earth, was the center of the solar system, had begun to take root in the late 16th century. However, it was Kepler who, through his application of mathematics and empirical observation, would bring Copernicus's vision to fruition and provide the empirical evidence needed to shift the course of scientific thought. Kepler's contributions were not limited to his famous laws of planetary motion. He was also instrumental in the development of modern optics, producing key insights into the nature of light and vision. Kepler's work with telescopes and his understanding of their use marked the beginning of the scientific approach to observational astronomy. Moreover, Kepler's application of mathematical principles to celestial phenomena represented a revolution in how humanity approached the natural world. He was one of the first to apply the rigor of mathematics to the study of the heavens, a practice that would become the hallmark of modern science. At the core of Kepler's scientific approach was a commitment to empirical observation. Unlike many of his predecessors, who adhered to abstract theories and speculation, Kepler emphasized the importance of careful observation and the use of mathematical reasoning to explain natural phenomena. His work was grounded in the data of his predecessor, Tycho Brahe, whose meticulous measurements of planetary positions provided the raw material for Kepler's breakthroughs. In many ways, Kepler's career can be seen as a confluence of earlier astronomical traditions, most notably that of Copernicus, and the emerging modern scientific methodology that would come to define the Enlightenment. However, Kepler's path to scientific greatness was not an easy one. He was born into a tumultuous world, both politically and personally. His early life was marked by hardship, including the death of his father when Kepler was just a child and his mother's involvement in a witchcraft trial later in life. Despite these early challenges, Kepler's intellectual abilities were apparent from a young age. His precociousness led him to study theology at the University of Tübingen, but it was his fascination with mathematics and astronomy that would ultimately guide him toward a career that defied the expectations of his time. Kepler's intellectual journey was shaped by the scientific climate of his era, which was undergoing a profound transformation. The Renaissance had revived interest in the works of ancient Greek and Roman scholars, and the Reformation had introduced new ways of thinking about the world. Kepler himself was deeply influenced by the heliocentric model of Copernicus, which, although controversial, presented a more accurate description of the solar system than the Ptolemaic geocentric model that had dominated for centuries. Kepler's embrace of the Copernican model would be critical to his later work, even though he did not fully accept all aspects of it at first. It was during his time as an assistant to Tycho Brahe, one of the greatest observational astronomers of the era, that Kepler made his most significant scientific breakthroughs. Brahe's detailed observations of planetary positions were crucial for Kepler's development of his laws of planetary motion. However, Kepler's relationship with Brahe was not without tension, as their personalities and scientific philosophies often clashed. Nevertheless, it was through their collaboration that Kepler was able to refine his ideas and develop a new understanding of the mechanics of the heavens. The publication of Kepler's first major work, Astronomia Nova, in 1609 marked the culmination of years of hard work and intellectual labor. In this work, Kepler introduced his first two laws of planetary motion, challenging centuries of accepted thinking. The first law stated that the orbits of planets are elliptical, not circular, as had been traditionally believed. The second law, known as the law of areas, described the way in which planets sweep out equal areas in equal times as they orbit the Sun. These discoveries were revolutionary, not just because they were scientifically accurate, but because they provided the first concrete evidence that the Copernican system was correct. Kepler's third law, published in Harmonics Mundi in 1619, further solidified his place in scientific history. This law, which relates the orbital periods of planets to their distances from the Sun, would later play a crucial role in the development of Newton's law of universal gravitation. Kepler's laws provided the empirical framework that would allow future astronomers to understand the mechanics of the solar system, and his work remains foundational to the study of celestial dynamics. Despite his extraordinary intellectual achievements, Kepler's life was not without personal and financial difficulties. He struggled with the realities of being a scientist in an age when patronage and support for scientific endeavors were far from guaranteed. Kepler's work was often undervalued in his own time, and his personal life was marked by hardship, including the deaths of his children and ongoing financial instability. Yet, despite these personal and professional setbacks, Kepler's intellectual legacy has endured. Johannes Kepler's legacy is one that continues to resonate in the fields of astronomy, physics, and mathematics. His work set the stage for the eventual development of Newtonian mechanics and revolutionized our understanding of the universe. Kepler's vision, perseverance, and application of mathematics to the study of the heavens helped to shift the course of scientific thought from a reliance on philosophical speculation to an empirical, data-driven approach. Kepler's story is not just one of scientific discovery, but of a man's unwavering commitment to understanding the cosmos, despite the many obstacles he faced along the way. Through his work, Johannes Kepler changed the way humanity viewed the universe, leaving a legacy that endures to this day. Johannes Kepler was born on December 27, 1571, in the small town of Walderstadt in the Holy Roman Empire, present-day Germany. He came into the world under a cloud of hardship, as his father, Heinrich Kepler, was a mercenary who had spent much of his life moving between various military campaigns, and his mother, Katharina, was a woman of strong religious beliefs. Though Johannes's early life was marked by financial instability and familial struggles, it was also shaped by a deep intellectual curiosity that would define the trajectory of his career. Kepler's childhood, marked by personal loss and economic instability, did not deter him from pursuing a life of intellectual rigor and scientific discovery. Kepler's family situation was precarious from the outset. His father was an itinerant soldier who, despite his initial promise of financial stability, failed to provide a consistent home life. His mother, Katharina, was later involved in a notorious witchcraft trial in the 1620s, which added another layer of strife to Kepler's already turbulent upbringing. The early loss of his father, followed by the loss of his mother to charges of witchcraft, contributed to Kepler's sense of isolation during his formative years. However, despite these personal tribulations, Kepler's intellect was nurtured by a strong educational foundation that would play a crucial role in shaping his future. Kepler's early education was centered in his hometown, where he was sent to the local Latin school. His exceptional intellect was recognized early on, and he showed a particular aptitude for mathematics and the natural sciences. Kepler's family, although not wealthy, understood the importance of education and did everything they could to support his intellectual development. His academic prowess earned him a scholarship to attend the University of Tübingen at the age of 14, marking the first major step in his journey toward becoming one of history's greatest scientists. At Tübingen, Kepler's interest in mathematics and astronomy deepened, and he soon found himself drawn to the works of Copernicus and other astronomers who were challenging the long-standing geocentric view of the universe. At Tübingen, Kepler studied a curriculum that combined theology, philosophy, and the sciences. Although he was originally trained as a theologian, Kepler's curiosity and analytical mind led him to pursue a more mathematical path. The academic atmosphere at Tübingen was one of intellectual ferment, with a strong emphasis on the study of Copernican heliocentrism, which argued that the Earth orbited the Sun rather than vice versa. This theory, though controversial at the time, was highly influential on Kepler's thinking. Kepler's studies at Tübingen exposed him to the works of great Renaissance scholars like Copernicus, as well as the mathematical advancements of figures such as Tycho Brahe, whose precise astronomical observations would later play a pivotal role in Kepler's own work. Kepler's exposure to the Copernican theory, which he encountered during his time at Tübingen, marked a decisive turning point in his intellectual development. Though Kepler initially accepted Copernicus's heliocentric model as a theoretical framework, he was not yet fully convinced of its correctness. Kepler's first major intellectual contribution was to attempt to reconcile Copernicus's theory with the observed motions of the planets, a task that would later lead him to his groundbreaking discovery of the elliptical orbits of planets. However, Kepler's initial exposure to heliocentrism also marked the beginning of a series of intellectual challenges. He was not content to merely accept the prevailing ideas of his time, but sought instead to improve and refine them through observation and mathematical reasoning. Kepler's interest in astronomy and mathematics was fueled by his desire to understand the underlying order of the universe. Unlike many of his contemporaries, Kepler was not content to rely solely on philosophical speculation or theological teachings to explain the natural world. Instead, he sought a more rigorous and empirical approach to understanding the heavens. This approach was greatly influenced by the mathematical rigor of Copernicus's model and the data gathered by Tycho Brahe. Kepler's early studies in mathematics, coupled with his philosophical and theological education, allowed him to see the deep connection between the physical world and mathematical principles. This belief in the harmony of the universe would shape much of his later work and lay the foundation for his discoveries in celestial mechanics. After completing his education at Tübingen, Kepler was appointed as a professor of mathematics at the University of Graz in 1594. This position marked the beginning of his professional career in the field of astronomy and mathematics. It was also at Graz that Kepler's early ideas began to take shape, particularly his efforts to reconcile the heliocentric model with the actual observations of planetary motions. Kepler's time at Graz was important not only because of his academic achievements, but also because of the social and political environment in which he worked. Graz, located in southern Austria, was a center of Protestant thought during a period of religious upheaval, and Kepler's own Protestant beliefs often put him at odds with the Catholic authorities. Kepler's years in Graz were marked by a sense of intellectual freedom, but they were also fraught with political and religious tensions. The Counter-Reformation, which sought to reassert Catholic dominance in Protestant areas, created an environment of religious conflict that made Kepler's work precarious. In 1599, after a religious dispute erupted in Graz, Kepler was forced to leave the city and move to Prague, where he would enter into a significant partnership with Tycho Brahe. The decision to relocate to Prague was a turning point in Kepler's career, as it brought him into close contact with the most important astronomer of the time, who would become his mentor and collaborator. Kepler's move to Prague marked the beginning of one of the most productive and transformative periods of his life. In Prague, Kepler became an assistant to Tycho Brahe, whose vast collection of astronomical data would prove invaluable to Kepler's work. Kepler's relationship with Brahe, however, was not without its complications. Brahe was a highly independent and sometimes difficult figure, and the two men often clashed over scientific methods and ideas. Nevertheless, their collaboration proved highly fruitful, as Brahe's precise observations allowed Kepler to formulate his laws of planetary motion. The synergy between Kepler's mathematical insights and Brahe's empirical data led to some of the most groundbreaking discoveries in the history of astronomy. Throughout his early education and professional experiences, Kepler's intellectual journey was characterized by a relentless pursuit of knowledge. His commitment to understanding the natural world through observation and mathematical analysis set him apart from many of his contemporaries. Kepler's journey from his early life in Walderstadt to his appointment in Graz and eventual collaboration with Brahe in Prague was marked by both personal hardship and intellectual triumph. It was during these formative years that Kepler laid the groundwork for the revolutionary discoveries that would later reshape humanity's understanding of the cosmos. Kepler's early life and education were instrumental in shaping his later work as one of the most important figures of the scientific revolution. His intellectual curiosity, driven by both his personal hardships and his deep fascination with the universe, propelled him to seek answers to some of the most profound questions of his time. From his childhood in Walderstadt to his years at the University of Tübingen and his work in Prague, Kepler's early experiences provided the foundation for his groundbreaking contributions to mathematics, astronomy, and science as a whole. Johannes Kepler's intellectual development was profoundly shaped by the works of earlier scholars, the social and political context of his time, and his personal encounters with some of the most prominent figures in the world of astronomy and mathematics. His scientific journey was not a solitary endeavor, but was instead a synthesis of ideas drawn from diverse sources, both ancient and contemporary. Among these influences, the heliocentric model of the universe, first proposed by Copernicus, and the observational data of Tycho Brahe stood out as the most critical elements in Kepler's intellectual formation. It was through the integration of these ideas, as well as his own rigorous mathematical analysis, that Kepler would go on to make groundbreaking contributions to our understanding of the cosmos. Kepler's earliest exposure to the idea of a heliocentric universe came during his time at the University of Tübingen, where the works of Copernicus were a significant part of the curriculum. Copernicus had published his seminal work, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, in 1543, challenging the traditional Ptolemaic geocentric model that had dominated Western thought for centuries. While Copernicus's ideas were controversial and initially met with resistance, they began to gain traction in intellectual circles by the time Kepler entered the academic world. Copernicus's heliocentric theory, which placed the sun at the center of the universe and suggested that the Earth and other planets revolved around it, provided the theoretical framework that Kepler would later build upon. However, Kepler did not accept Copernicus's model uncritically. While he embraced the idea of a heliocentric universe, he was deeply concerned with the model's reliance on circular orbits, which were seen as perfect geometric forms. Kepler, whose mathematical training had given him a keen sense of the limitations of idealized models, found that Copernicus's system, despite its elegance, did not adequately explain the observed motions of the planets. It was this dissatisfaction with the imperfections of the Copernican system that led Kepler to search for a more accurate model, one that would ultimately challenge centuries of astronomical tradition. In this respect, Kepler's work represented a shift from philosophical speculation to a more empirical and mathematical approach to understanding the heavens. One of the most significant intellectual influences on Kepler was the work of the Danish astronomer Tycho Brahe, with whom he would later collaborate. Brahe was renowned for his extraordinarily precise measurements of planetary positions, which had been recorded over many years using a series of instruments he had designed himself. These data were crucial for Kepler, who had inherited Brahe's astronomical records after being appointed as his assistant in Prague in 1600. Although Brahe himself adhered to a geoheliocentric model, where the sun revolved around the Earth, but the planets revolve around the sun, his observational data were invaluable for Kepler, who sought a purely heliocentric explanation of planetary motion. Brahe's meticulous attention to detail and his ability to gather empirical data would become the foundation for Kepler's later breakthroughs. Kepler's intellectual debt to Brahe was profound, not only because of the invaluable data that Brahe provided, but also due to Brahe's influence on Kepler's scientific philosophy. Brahe, though a staunch opponent of the Copernican system, had an empirical mindset that emphasized the importance of careful observation and the rejection of purely speculative theories. Kepler, in turn, absorbed these principles and applied them to his own work, allowing him to move beyond the limitations of Copernican theory and towards his own revolutionary discoveries. In many ways, Brahe's empirical methods provided Kepler with the tools he needed to refine and eventually replace the geometric models of the universe with a more accurate, observationally based understanding. Despite their differences, Kepler and Brahe's collaboration proved mutually beneficial. Kepler's ability to interpret Brahe's observational data through the lens of mathematics allowed him to make sense of the apparent discrepancies between the Copernican model and Brahe's observations. Kepler's talent for mathematical analysis enabled him to take the raw data and, through a series of calculations, develop a more refined model of planetary motion. It was during this time that Kepler began to formulate his laws of planetary motion based on Brahe's data, which would forever change the way scientists understood the motion of celestial bodies. Kepler's intellectual development was also heavily influenced by the intellectual climate of his time. The late 16th and early 17th centuries were a period of intense scientific and philosophical upheaval. The scientific revolution, which had gained momentum with the work of figures like Galileo Galilei and Copernicus, was challenging traditional Aristotelian views of the universe. In particular, the shift from a geocentric to a heliocentric understanding of the solar system represented a radical departure from centuries of accepted wisdom. This shift was part of a broader movement that emphasized the role of observation, experimentation, and mathematical reasoning in understanding the natural world, principles that Kepler wholeheartedly embraced. Kepler's intellectual development was also shaped by his deep interest in the writings of earlier mathematicians and philosophers. The ancient Greeks, particularly Plato and Pythagoras, had a profound influence on his thinking. Kepler was deeply inspired by the idea of a harmonious and mathematically ordered universe, an idea that had been espoused by Pythagoras and his followers. Kepler believed that the underlying order of the universe could be expressed through mathematical relationships, and this belief would guide much of his work. His search for mathematical patterns in the motion of the planets was driven by the conviction that the universe was not chaotic, but instead governed by rational and harmonious principles that could be uncovered through careful observation and calculation. In addition to ancient Greek philosophy, Kepler was also influenced by the work of Renaissance thinkers such as Nicholas Copernicus, Tycho Brahe, and Galileo Galilei. These figures, along with others, were part of a larger intellectual movement that sought to break free from the constraints of medieval scholasticism and to develop a new, empirical approach to science. Kepler's work was deeply embedded in this intellectual tradition, and he was profoundly influenced by the idea that the natural world could be understood through observation, experimentation, and mathematics. His willingness to challenge established ideas and to look for new ways to understand the cosmos made him a key figure in the development of modern science. In addition to the intellectual influences that shaped his scientific work, Kepler's religious beliefs also played an important role in his intellectual development. Kepler was a devout Lutheran, and his faith in the divine order of the universe was central to his worldview. He believed that the natural world was a reflection of God's creation, and that by understanding the laws of nature, he was uncovering the divine plan for the universe. This belief in the harmony of the cosmos fueled Kepler's search for mathematical patterns in the motion of the planets. He saw the task of understanding the universe as both a scientific and a spiritual endeavor, and his work was motivated by a sense of awe and reverence for the natural world. Kepler's intellectual development was a dynamic and multifaceted process, shaped by a wide range of influences, from the work of earlier astronomers and philosophers to the intellectual climate of the scientific revolution. His willingness to integrate ideas from diverse sources, coupled with his commitment to empirical observation and mathematical reasoning, allowed him to make groundbreaking contributions to our understanding of the universe. Kepler's ability to synthesize ideas, along with his perseverance in the face of challenges, was a key factor in his success as a scientist and his lasting impact on the field of astronomy. Through his work, Kepler not only advanced our understanding of planetary motion, but also helped to lay the foundation for the modern scientific worldview. Kepler's intellectual trajectory took a decisive turn when he became involved with the work of Tycho Brahe, a Danish astronomer whose contributions to observational astronomy were unprecedented in the late 16th century. Although Brahe himself was a staunch opponent of the Copernican heliocentric model, his rigorous, empirical observations of the planets provided the raw data that Kepler would ultimately use to revolutionize our understanding of the cosmos. The collaboration between Kepler and Brahe, though marked by tension and differences in scientific approach, formed the crucible in which Kepler's laws of planetary motion were forged. The path to Kepler's association with Brahe began in 1599 when Kepler was appointed as Brahe's assistant in Prague. Prior to this, Kepler had already established a reputation as an astronomer and mathematician, thanks in large part to his earlier work in Graz. In his role as a professor of mathematics, Kepler had published Mysterium Cosmographicum in 1596, a work in which he sought to explain the structure of the solar system through the geometry of nested platonic solids. Although his arguments for the arrangement of the planets were not fully accepted, the book nonetheless demonstrated Kepler's ability to blend mathematics and astronomy in novel ways. His interest in the heavens had long been focused on understanding the geometry of planetary orbits, and this would soon become the central focus of his work. Kepler's invitation to work with Brahe was both an honor and a turning point in his career. Brahe had achieved international fame for his highly accurate observations of the planets, particularly Mars, and he had spent years constructing complex astronomical instruments that allowed him to measure the positions of celestial bodies with unprecedented precision. Brahe's data, collected over several decades, were considered to be some of the most reliable in the field of astronomy. While Brahe's model of the solar system, which was a geoheliocentric system that placed the Earth at the center, was at odds with the Copernican heliocentric model that Kepler championed, the empirical rigor of Brahe's observations was invaluable to Kepler's own work. Despite their differing views on the structure of the cosmos, Brahe and Kepler's collaboration proved essential for the advancement of Kepler's own theories. Brahe, though skeptical of Copernican heliocentrism, was a keen observer and did not hesitate to engage with those who could make sense of his observations. Kepler, for his part, was keen to reconcile Brahe's empirical data with the Copernican system, even if it meant challenging the prevailing models of planetary motion. In 1600, after Brahe's death, Kepler inherited his vast archive of observational data, which included a particularly valuable series of measurements related to the planet Mars. These data would serve as the foundation for Kepler's groundbreaking work on the elliptical orbits of planets. The Mars data were especially crucial for Kepler's development of his laws of planetary motion. Brahe's observations had been taken over several years and allowed for an extraordinary level of precision in the measurement of Mars's trajectory across the sky. However, Brahe's model, with its reliance on circular orbits, could not account for the complex behavior of Mars, which appeared to wander in and out of retrograde motion as observed from Earth. This anomaly was a significant challenge for astronomers, as the Ptolemaic and Copernican models both relied on circular orbits, which could not explain the observed intricacies of Mars's motion. Kepler's challenge was to find a model that could account for these discrepancies without resorting to the overly complex system of epicycles used by earlier astronomers. Kepler's approach to solving this problem was methodical and deeply mathematical. Using Brahe's data, he worked for months to compute the best possible fit for Mars's orbit. Through a painstaking process of trial and error, Kepler eventually discovered that the orbit of Mars could be described not as a perfect circle, as had been traditionally assumed, but as an ellipse. This realization, which Kepler presented in his work Astronomia Nova in 1609, marked a profound shift in astronomical thinking. It not only refuted the long-standing belief in the perfection of circular orbits, but also laid the foundation for Kepler's first law of planetary motion, that the planets move in elliptical orbits with the Sun at one focus. Kepler's discovery of elliptical orbits was revolutionary because it fundamentally altered the way astronomers thought about planetary motion. For centuries, the prevailing belief had been that the heavens were governed by perfect, unchanging forms, with circular orbits being the epitome of geometric perfection. Kepler's insight that the planets' orbits were elliptical with varying distances from the Sun at different points in their orbits, was a dramatic departure from this Aristotelian ideal. This discovery suggested that the natural world was not driven by divine perfection, but by a more complex, dynamic system that could be understood through observation and mathematical analysis. The realization of elliptical orbits was just the beginning of Kepler's work on planetary motion. He soon went on to formulate his second law of planetary motion, which he described in Astronomia Nova. This law, known as the law of areas, stated that a line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. In other words, the closer a planet is to the Sun, the faster it moves, and the farther it is, the slower it travels. This law was a direct consequence of the elliptical nature of planetary orbits and provided a more accurate description of planetary motion than any previous models. Kepler's second law not only refined the understanding of planetary movement, but also hinted at deeper principles governing the dynamics of the solar system. Kepler's third law, which he formulated a decade later in Harmonics Mundi, 1619, completed his set of laws of planetary motion. This law, which relates the periods of revolution of planets to their distances from the Sun, was perhaps the most significant of all. Kepler demonstrated that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. This relationship not only provided a more precise understanding of the relationships between planetary orbits, but also laid the groundwork for Newton's later development of the law of universal gravitation. The third law effectively unified Kepler's earlier insights into a single, coherent framework that described the motion of all the planets in the solar system. The collaboration with Tycho Brahe thus proved to be the critical turning point in Kepler's career. Without Brahe's data, Kepler would not have been able to make the discoveries that would later form the foundation of celestial mechanics. Brahe's data provided the raw material for Kepler's mathematical genius, and their combined efforts led to the first truly accurate description of planetary motion. Although their relationship was often fraught with tension, Brahe was skeptical of Kepler's heliocentric beliefs, and Kepler was frustrated by Brahe's refusal to accept the Copernican system. Their partnership produced some of the most significant astronomical advancements of the era. In retrospect, Kepler's work with Brahe represented a critical phase in the history of science, as it marked the transition from a reliance on idealized geometric models to a more empirical, data-driven approach to understanding the universe. Kepler's ability to take Brahe's observational data and apply his own mathematical reasoning to it allowed him to uncover the true nature of planetary motion. This shift in methodology, from speculation to empirical verification, was one of the key developments that characterized the scientific revolution, and Kepler's work in this regard remains foundational to modern astronomy. The culmination of Johannes Kepler's work on planetary motion came with the formulation of his three laws, which forever altered the trajectory of astronomical theory. Kepler's laws of planetary motion, derived from his detailed analysis of the astronomical data provided by Tycho Brahe, were groundbreaking in both their mathematical rigor and their departure from the classical Aristotelian worldview. These laws not only provided a more accurate description of planetary motion, but also laid the foundation for the later work of Sir Isaac Newton and the development of classical mechanics. Understanding the development and significance of Kepler's laws requires an exploration of the intellectual climate of his time, the scientific context in which he worked, and the meticulous process by which he arrived at these revolutionary ideas. Kepler's first law, which states that planets move in elliptical orbits with the Sun at one focus, was a radical departure from the prevailing belief in perfect circular orbits. Prior to Kepler, astronomers, following the teachings of Aristotle and Ptolemy, held that the heavens were composed of perfect and immutable circles. The idea of circular orbits had a long-standing tradition in Western thought, dating back to the ancient Greek philosophers, who viewed circles as the epitome of geometric perfection. This belief was perpetuated in the Copernican model, which placed the Sun at the center of the universe, but still relied on circular orbits to describe the motion of the planets. Kepler's first law, based on Tycho Brahe's data, shattered this long-standing assumption. Through painstaking analysis, Kepler discovered that the orbit of Mars, and by extension the orbits of all the planets, were not circular but elliptical in shape. The ellipse, unlike the circle, has two foci, and the Sun occupies one of these foci. This discovery not only rendered the idea of perfect, unchanging celestial spheres obsolete, but also introduced a new way of thinking about planetary motion, one that was based on empirical data and geometric analysis rather than on metaphysical or theological assumptions. Kepler's first law was thus a radical break from centuries of astronomical tradition and a triumph of observation and mathematics. The second law, known as the law of areas, was the natural consequence of the first law. Kepler's second law states that a line drawn from a planet to the Sun sweeps out equal areas in equal periods of time. In other words, a planet moves faster in its orbit when it is closer to the Sun and slower when it is farther away. This discovery had profound implications for our understanding of the dynamics of planetary motion. The law of areas showed that the speed of a planet's motion was not constant, but varied depending on its distance from the Sun. It was a direct result of the elliptical nature of planetary orbits, where the planet's distance from the Sun changes as it moves along its orbital path. Kepler's second law challenged the earlier models of planetary motion, which assumed that planets moved at a constant speed throughout their orbits. The Ptolemaic and Copernican models, despite their differences, both relied on the idea that the planets moved in uniform circular orbits. The law of areas, however, introduced a new understanding of planetary motion, one that was more complex and dynamic, reflecting the fact that the force of gravity between the planets and the Sun caused their speeds to vary depending on their positions in the orbit. This insight into the nature of planetary motion was a precursor to the later work of Isaac Newton, who would go on to explain the underlying force of gravity responsible for these variations in planetary speed. The third law, perhaps the most famous of Kepler's contributions, relates the periods of revolution of the planets to their average distances from the Sun. Kepler's third law states that the square of the orbital period of a planet is proportional to the cube of its average distance from the Sun. This law provided a simple and elegant formula that described the relationship between a planet's orbital period and its distance from the Sun. For example, Kepler's third law showed that a planet like Earth, which is closer to the Sun, has a shorter orbital period than a planet like Jupiter, which is farther away. This relationship helped to establish a more accurate understanding of the distances between the planets and their relative motion around the Sun. Furthermore, the third law was a critical step towards the unification of celestial and terrestrial mechanics, a task that would be completed by Newton in the 17th century. Kepler's laws of planetary motion represented a profound shift in the way that scientists viewed the universe. Prior to Kepler, the prevailing view, influenced by Aristotle and Ptolemy, was that the heavens were perfect and unchanging, governed by idealized, circular orbits. Kepler's work shattered this notion by showing that the planets move in elliptical orbits, that their speed varies depending on their distance from the Sun, and that there is a mathematical relationship between their distance from the Sun and the time it takes them to complete an orbit. These laws were the first true scientific laws of motion and laid the groundwork for the development of Newtonian mechanics. Kepler's laws also marked a shift from philosophical, metaphysical understanding of the universe to a more empirical, data-driven approach. Kepler's ability to use Tycho Brahe's precise observational data and apply rigorous mathematical methods to develop his laws demonstrated the power of the scientific method. Whereas earlier astronomers had relied on speculation and philosophical reasoning to explain celestial phenomena, Kepler's work was based on empirical evidence and mathematical reasoning. This marked a key turning point in the history of science, as it heralded the rise of a more scientific and experimental approach to understanding the natural world. Although Kepler's laws were groundbreaking, they were not immediately accepted by all of his contemporaries. The idea of elliptical orbits, in particular, met with resistance from some astronomers who continued to cling to the belief in perfect circular orbits. However, Kepler's laws gained wider acceptance over time, especially as they were further validated by the observations of later astronomers, including Isaac Newton. Newton, in particular, was able to build on Kepler's work by providing a physical explanation for the elliptical orbits of the planets through his law of universal gravitation. Newton's work in the 17th century ultimately confirmed Kepler's laws and provided a theoretical framework for understanding the forces that govern planetary motion. Despite the initial resistance to his ideas, Kepler's laws of planetary motion would eventually become the cornerstone of modern astronomy. They not only provided a more accurate description of planetary motion, but also helped to shape the way scientists thought about the universe. Kepler's work demonstrated the power of mathematical reasoning and empirical observation, and it laid the foundation for the scientific revolution that would transform our understanding of the natural world. His laws of planetary motion were among the most important achievements in the history of science, and they continue to be essential to the study of astronomy today. In addition to their scientific importance, Kepler's laws also had philosophical implications. Kepler himself believed that the mathematical order he uncovered in the motions of the planets reflected a divine harmony in the cosmos. For Kepler, the study of the heavens was not only a scientific endeavor, but also a spiritual one. He saw the universe as a reflection of God's divine plan, and his work was motivated by a desire to uncover the hidden order of the cosmos. In this sense, Kepler's laws were not just scientific principles, but also expressions of his belief in the harmony and order of creation. Kepler's laws of planetary motion represent one of the most important intellectual achievements of the scientific revolution. Through his careful analysis of Tycho Brahe's data, Kepler was able to formulate 3 laws that transformed our understanding of the universe. These laws not only provided a more accurate description of planetary motion, but also laid the groundwork for the later development of Newtonian mechanics. Kepler's work was a turning point in the history of science, marking the shift from a reliance on speculative models to a more empirical, data-driven approach to understanding the natural world. His laws continue to be fundamental to modern astronomy, and his legacy as one of the founders of modern science remains secure. The work of Johannes Kepler did not occur in isolation. His discoveries and theories emerged in the context of the broader scientific revolution, a period during the 16th and 17th centuries when the foundations of modern science were laid. This intellectual transformation, which also saw the contributions of figures like Galileo Galilei, Francis Bacon, and Isaac Newton, would permanently alter humanity's understanding of the natural world. Kepler's laws of planetary motion were central to this revolution, providing a model for how empirical observation, mathematical reasoning, and theoretical explanations could be combined to reveal the workings of the universe. Kepler's embrace of the Copernican heliocentric model marked a clear break from the geocentric universe that had dominated Western thought for over 1,000 years. This shift was part of a broader trend in the scientific revolution, in which traditional Aristotelian views of the cosmos were increasingly questioned and replaced by new, more empirical theories. While Copernicus had introduced the heliocentric theory of the solar system, it was Kepler who provided the mathematical framework for it to be fully understood and accepted. His laws of planetary motion confirmed the heliocentric model as the correct representation of the solar system, and they served as a foundation for later developments in physics and astronomy. One of the key aspects of Kepler's contribution to the scientific revolution was his insistence on the importance of observation and data. At a time when much of astronomy relied on philosophical speculation and abstract reasoning, Kepler's methods were deeply empirical. His work was based on the precise astronomical observations of Tycho Brahe, which he meticulously analyzed and compared in order to derive his laws of planetary motion. By placing such a strong emphasis on empirical evidence, Kepler set a precedent for later scientists to ground their theories in data, a practice that became fundamental to the development of modern science. Kepler's work also exemplified the growing importance of mathematics in the scientific revolution. Prior to Kepler, many of the theories of planetary motion were grounded in qualitative explanations that relied on concepts like divine perfection or celestial spheres. However, Kepler's laws demonstrated that the motions of the planets could be described with mathematical precision, a breakthrough that would have profound implications for the development of physics and astronomy. Kepler's use of mathematics to describe the natural world was a crucial step toward the eventual unification of celestial and terrestrial mechanics, a project that would be fully realized by Isaac Newton later in the century. The relationship between Kepler's laws and the work of Galileo Galilei is another important aspect of the scientific revolution. Galileo's use of the telescope to observe the moons of Jupiter and the phases of Venus provided critical evidence in support of the Copernican heliocentric model. Galileo's observations, along with Kepler's mathematical laws, helped to solidify the idea that the Earth was not the center of the universe. However, while Galileo's work was instrumental in confirming the heliocentric theory, it was Kepler's laws that provided the detailed mathematical framework necessary to understand the mechanics of planetary motion. Together, Kepler and Galileo formed a complementary pair, with Kepler providing the theoretical foundation and Galileo offering empirical evidence. Despite their shared commitment to the Copernican system, Kepler and Galileo differed in their approaches to science. Galileo, with his focus on experimentation and empirical observation, was often more concerned with demonstrating the practical effects of natural phenomena. Kepler, on the other hand, was primarily focused on uncovering the underlying mathematical relationships that govern the motion of celestial bodies. This philosophical distinction between the two men reflects the diversity of approaches that characterized the scientific revolution, where different scientists brought their own methods and perspectives to the task of understanding nature. Nonetheless, both Kepler and Galileo played critical roles in the overthrow of the Aristotelian worldview and the establishment of a new scientific paradigm. Another important aspect of Kepler's work in the context of the scientific revolution was his approach to the nature of the universe. Kepler believed that the universe was governed by a divine, rational order that could be understood through mathematics. In his Harmonics Mundi, 1619, Kepler explored the idea that the motions of the planets were not just random or mechanical, but reflected a deep, underlying harmony that could be expressed in musical terms. This concept, which came to be known as the music of the spheres, was a reflection of Kepler's belief that the universe was not chaotic, but rather governed by a set of natural laws that could be uncovered through reason and mathematical analysis. Kepler's religious and philosophical beliefs, while distinct from those of later scientists like Newton, were integral to his scientific worldview and influenced his approach to research. Kepler's contribution to the scientific revolution was not only important for its immediate impact on astronomy, but also for its longer-term influence on the development of science as a whole. Kepler's work demonstrated the power of the scientific method, which involved the systematic collection of data, the formulation of hypotheses, and the testing of those hypotheses through observation and experimentation. This method would later be refined and expanded by figures like Francis Bacon and René Descartes, and it would become the cornerstone of modern scientific inquiry. Kepler's work also helped to establish the idea that scientific theories should be based on empirical evidence and mathematical reasoning, principles that remain central to the scientific enterprise today. In addition to its immediate impact on astronomy, Kepler's work also laid the groundwork for the development of classical mechanics. Kepler's laws describe the motion of the planets with remarkable precision, but they did not explain the underlying forces that caused the planets to move in the way that they did. It was Isaac Newton, building on Kepler's work, who would provide a physical explanation for the motions of the planets in his Principia Mathematica, 1687, in which he formulated the law of universal gravitation. Newton's law of gravity explained why planets followed elliptical orbits and provided the theoretical framework that unified Kepler's laws with terrestrial mechanics. Kepler's contribution to this process was immense. Without his laws, Newton's theory of gravitation would not have been possible. Kepler's influence also extended beyond the realm of astronomy. His work on the mathematical description of planetary motion inspired future generations of scientists and mathematicians. Kepler's insistence on the importance of mathematics in understanding the natural world was a key element of the scientific revolution and would later influence the work of mathematicians such as Pierre-Simon Laplace, Carl Friedrich Gauss, and Albert Einstein. Kepler's laws were not just important for their immediate impact on astronomy. They also served as a model for how scientific inquiry could lead to deeper, more universal truths about the cosmos. Furthermore, Kepler's legacy was not confined to the scientific community. His work had a broader cultural impact, influencing philosophical and religious thought in addition to the sciences. Kepler's belief in a rational, mathematical order to the universe resonated with the broader intellectual currents of the time, which sought to reconcile the discoveries of science with religious and metaphysical ideas. Kepler's fusion of science and spirituality, along with his view of the universe as a harmonious, divine creation, helped to pave the way for later thinkers who sought to understand the universe both scientifically and philosophically. Johannes Kepler's work was central to the scientific revolution, both for its immediate impact on astronomy and for its longer-term influence on the development of modern science. Kepler's laws of planetary motion, based on the detailed observational data of Tycho Brahe, provided a mathematical framework for understanding the movement of the planets and helped to confirm the Copernican heliocentric model. Kepler's emphasis on empirical observation, mathematical reasoning, and the unification of celestial and terrestrial mechanics was instrumental in the establishment of the scientific method and the rise of modern science. His work influenced generations of scientists, culminating in the theories of Isaac Newton, and continues to shape our understanding of the universe today. Through his groundbreaking contributions to astronomy and his broader impact on the scientific worldview, Kepler's legacy as a key figure in the scientific revolution remains secure. Johannes Kepler's contributions to astronomy, particularly his laws of planetary motion, were not only foundational to the field of celestial mechanics, but also had a profound and lasting impact on the development of physics. While Kepler's work was primarily focused on understanding the motion of the planets, the mathematical precision and empirical rigor he applied in his analysis laid the groundwork for later advancements in physics, particularly the development of Newtonian mechanics. Kepler's ability to describe planetary motion through mathematical relationships was a key moment in the evolution of scientific thought, ushering in an era where empirical data and mathematical equations became central to understanding natural phenomena. This chapter will explore how Kepler's work influenced the development of physics, specifically in terms of its impact on the study of motion, the forces governing it, and the eventual formulation of the laws of motion by Isaac Newton. Kepler's laws of planetary motion were groundbreaking not only because they described the orbits of planets in precise mathematical terms, but also because they introduced the idea that celestial bodies obeyed the same physical principles as objects on Earth. Before Kepler, the motion of the planets was seen as part of a divine, perfect order, governed by philosophical and theological concepts rather than physical forces. By demonstrating that planetary motion followed specific mathematical laws, Kepler paved the way for the idea that the entire universe, both celestial and terrestrial, was governed by universal principles that could be described and predicted mathematically. This shift from a metaphysical to a physical understanding of the cosmos was a key milestone in the history of physics. The most direct connection between Kepler's work and later developments in physics was the influence he had on Isaac Newton. Newton's Principia Mathematica, 1687, in which he formulated the law of universal gravitation and the three laws of motion, was deeply indebted to Kepler's laws. Kepler had demonstrated that planets moved in elliptical orbits and that their motion could be described by mathematical relationships, but he did not explain the underlying causes of these motions. Newton, building on Kepler's work, was able to provide a physical explanation for the elliptical orbits by proposing that planets were attracted to the sun by a force of gravity. Newton's work showed that the same force that caused an apple to fall to the ground also governed the motion of celestial bodies. In this way, Kepler's mathematical description of planetary motion was a critical step in the development of Newtonian physics, which sought to explain both terrestrial and celestial motion under a unified set of laws. In addition to providing the foundation for Newtonian mechanics, Kepler's work also contributed to the broader development of the scientific method in physics. Kepler's emphasis on empirical observation, precise measurements, and mathematical analysis was a model for how physics would be approached in the centuries to come. Whereas earlier physicists and natural philosophers relied heavily on qualitative reasoning and speculative models, Kepler's approach marked a decisive turn toward the use of quantitative methods to describe natural phenomena. This emphasis on measurement and data-driven analysis would become central to the development of modern physics, particularly in the fields of mechanics, electromagnetism, and thermodynamics. Kepler's impact on physics can also be seen in the way he influenced the study of motion. His second law, which states that a planet sweeps out equal areas in equal times, introduced the idea that the speed of an object is not constant, but can change depending on its position in its orbit. This principle was later generalized by Newton and applied to all objects, both celestial and terrestrial. Newton's first law of motion, which states that an object in motion will remain in motion unless acted upon by an external force, is closely related to Kepler's idea that planetary motion follows a predictable mathematical pattern. Kepler's work laid the groundwork for understanding that objects move in a consistent, predictable manner governed by certain forces, and this idea would be central to the development of classical mechanics. Furthermore, Kepler's work had a lasting impact on the study of gravitational forces. While Kepler himself did not identify gravity as the force behind planetary motion, his laws made it clear that there was an invisible force that governed the planet's motion around the sun. This insight was crucial for Newton, who would go on to formulate the law of universal gravitation. Newton's law of gravity posits that every particle in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This law, which explains both the motion of celestial bodies and the behavior of objects on Earth, was a direct extension of Kepler's insights into the nature of planetary motion. Without Kepler's empirical work, Newton's formulation of the law of universal gravitation would have been impossible. Kepler's contributions also had an impact on the study of orbital mechanics, which later became a crucial field of physics. Orbital mechanics, the study of the motion of objects in space under the influence of gravitational forces, relies heavily on Kepler's laws. The understanding that planets move in elliptical orbits, that their speed varies depending on their distance from the Sun, and that the relationship between the period of a planet's orbit and its distance from the Sun can be described mathematically, are fundamental principles in the study of space travel and satellite motion today. Kepler's laws continue to be used by engineers and scientists in the design of spacecraft trajectories, the calculation of satellite orbits, and the study of the motion of comets and asteroids. Another area where Kepler's work influenced the development of physics was in the field of energy and work. Kepler's third law, which relates the period of a planet's orbit to its average distance from the Sun, was one of the first instances in which the relationship between motion and energy was expressed mathematically. Though Kepler did not have the concept of energy as we understand it today, his recognition that the motion of planets was related to their distance from the Sun laid the groundwork for later developments in the understanding of kinetic and potential energy. Newton's laws of motion, which are based on the principles of conservation of momentum and energy, directly built on Kepler's insights into planetary motion and provided the theoretical framework for understanding energy in both celestial and terrestrial mechanics. Kepler's impact on physics also extended to the development of the concept of force. While Kepler did not have a fully developed theory of force, his work demonstrated the need for an invisible force that could explain the motion of celestial bodies. This idea was eventually formalized by Newton, who formulated his laws of motion and law of gravity to describe the forces acting on objects. Newton's second law of motion, which states that the force acting on an object is equal to its mass times its acceleration, was a direct extension of the concepts that Kepler introduced in his laws of planetary motion. Kepler's work thus played a pivotal role in the development of the concept of force as a fundamental quantity in physics. Kepler's contribution to the development of physics was not solely theoretical. His emphasis on the use of accurate measurements and observation techniques influenced the way physics would be practiced. Kepler himself was known for his meticulous and careful measurements of planetary positions, which allowed him to derive his laws with a high degree of precision. This commitment to accurate data collection set a standard for future physicists, who would follow Kepler's example in their own research. The modern scientific approach to physics, with its reliance on careful experimentation, measurement, and observation, owes much to Kepler's pioneering work. Finally, Kepler's impact on physics can be understood in terms of his legacy as a figure who bridged the gap between the ancient and modern worlds of science. His work represented a synthesis of the early traditions of astronomy, grounded in a belief in celestial harmony and divine order, with the emerging empirical methods of the scientific revolution. Kepler's ability to blend these two traditions and his willingness to challenge long-held beliefs about the nature of the universe made him a key figure in the transition from medieval to modern physics. His work paved the way for the great advances of the 17th century and beyond, shaping the trajectory of scientific inquiry in a way that continues to resonate today. Kepler's influence on the development of physics was profound and far-reaching. His laws of planetary motion, grounded in rigorous observation and mathematical analysis, helped to establish the foundational principles of classical mechanics and provided the framework for Newton's laws of motion and the law of universal gravitation. Kepler's work also contributed to the development of key concepts in physics, including energy, force, and orbital mechanics, and set the stage for later advancements in the study of motion and gravitation. His emphasis on empirical data, mathematical reasoning, and the unification of celestial and terrestrial mechanics marked a decisive shift in the way that science, particularly physics, will be practiced in the future. Kepler's legacy as a pioneer of modern physics is secure, and his work continues to influence the way we understand the forces that govern the universe. Johannes Kepler's contributions to science were profound, but his relationship with religion and spirituality played a significant role in shaping his worldview and approach to scientific inquiry. In many ways, Kepler's faith was deeply intertwined with his scientific work. While modern science is often thought of as being separate from religious beliefs, in Kepler's time, the two were not seen as mutually exclusive. Kepler was a devout Lutheran, and his religious beliefs shaped his understanding of the universe and his motivations as a scientist. This chapter explores how Kepler's spirituality influenced his scientific work, his vision of the cosmos, and the way he reconciled his religious convictions with the emerging scientific paradigm of the early 17th century. Kepler believed that the universe was created according to a rational, mathematical order, and that this order reflected the divine will. In his writings, he frequently referred to the idea that the cosmos was a reflection of God's perfection. He saw his scientific work not as a departure from his religious beliefs, but as an attempt to understand and uncover the divine structure of the universe. For Kepler, studying the motions of the planets and understanding the physical laws governing the cosmos were ways to gain insight into the mind of God. In this sense, Kepler's scientific work was an act of worship, a way of appreciating and uncovering the beauty of God's creation. Kepler's religious beliefs were influenced by the Protestant Reformation, which had introduced new ways of thinking about the relationship between God and the universe. The Reformation emphasized the importance of personal interpretation of Scripture and the belief that the natural world could provide evidence of God's work. Kepler, influenced by the ideas of Martin Luther and other reformers, saw the study of the natural world as a way to understand divine truths. For him, the laws of nature were not arbitrary, but rather were part of a divine plan that could be uncovered through reason and empirical observation. Kepler's view of the cosmos as a reflection of divine order was not unique to him, but was part of a broader intellectual trend in which many early scientists, particularly those influenced by the Reformation, saw science as a way of understanding God's design. Kepler's religious beliefs also influenced his approach to the Copernican heliocentric model of the universe. While Kepler was one of the most enthusiastic advocates of Copernicus' ideas, he was also deeply concerned with reconciling the heliocentric model with his Christian faith. Kepler believed that the heliocentric theory, which posited that the Earth revolved around the Sun, was not in conflict with Scripture. In fact, he argued that the heliocentric model better reflected the divine order of the universe. Kepler viewed the Sun as the central, most important body in the cosmos, and he believed that the Earth's motion around the sun was a sign of the divine harmony of the universe. For Kepler, the heliocentric model was a way of seeing God's creation more clearly and more accurately, and he worked tirelessly to demonstrate its validity through his mathematical analysis. In addition to his belief in the divine order of the universe, Kepler was also deeply influenced by the idea of cosmic harmony. This belief was rooted in ancient Greek philosophy, particularly in the work of Pythagoras and Plato, who saw the universe as governed by mathematical ratios and harmonies. Kepler was fascinated by the idea that the movements of the planets could be described by mathematical formulas that expressed a deeper, harmonious structure. In his work Harmonics Mundi, 1619, Kepler explored the concept of the music of the spheres, the idea that the planets' orbits produced a cosmic harmony akin to musical intervals. This idea was rooted in Kepler's belief that the universe, in its mathematical precision, reflected a divine order that could be understood and appreciated through the study of mathematics and geometry. Kepler's belief in the divine order of the universe also led him to reject the idea of randomness or chaos in nature. He was deeply opposed to the idea that the motions of the planets were purely mechanical or arbitrary. Instead, Kepler believed that the planets moved in elliptical orbits according to divine laws that reflected the harmony and order of the cosmos. This view contrasted sharply with the Aristotelian worldview, which held that the heavens were made up of perfect, unchanging spheres, and that celestial motion was a reflection of divine perfection. Kepler's rejection of this idea and his insistence on a mathematical description of planetary motion represented a shift away from the metaphysical explanations of the cosmos toward a more empirical, mathematically grounded understanding. Despite his strong religious convictions, Kepler's work was not without controversy, particularly in relation to his views on astrology. Kepler's belief in the interconnectedness of the cosmos led him to embrace astrology as a valid science, at least to some extent. He believed that the positions of the planets could have an influence on earthly events, and he even wrote horoscopes for various individuals. However, Kepler's approach to astrology was distinct from that of many of his contemporaries. Unlike many astrologers of the time, who relied on arbitrary and mystical interpretations of celestial events, Kepler sought to ground astrology in mathematical and astronomical principles. He attempted to create a more scientific and rational approach to astrology, using the data from his astronomical observations to predict the movements of the planets and their effects on Earth. While Kepler's involvement in astrology may seem at odds with his scientific work, it is important to understand it within the context of the time. Astrology was widely regarded as a legitimate discipline during the early 17th century, and many scientists, including Tycho Brahe and Galileo Galilei, also practiced astrology to some degree. Kepler's work, while deeply influenced by his religious beliefs, also marked a shift in the way that science and religion were viewed. In the medieval and Renaissance periods, science was often seen as a way to understand and interpret God's will, but it was also frequently in conflict with religious authorities. By the time of Kepler, the relationship between science and religion had become more complex, with figures like Galileo challenging the authority of the Church. Kepler, however, did not see his scientific work as in conflict with his faith. Instead, he viewed his scientific endeavors as a way to better understand the divine order of the universe. Kepler's conviction that science and religion were compatible helped to lay the foundation for later thinkers, such as Isaac Newton, who also believed in the unity of science and religion. Kepler's religious views also shaped his interactions with others in the scientific community. While Kepler was deeply devoted to his faith, he was not averse to challenging traditional religious beliefs when they conflicted with his scientific findings. For example, he rejected the traditional belief in the perfection of celestial spheres, which was based on the idea that the heavens were immutable and unchanging. Instead, Kepler argued that the planets' elliptical orbits were a better representation of the divine order of the universe. This willingness to challenge established religious ideas in favor of empirical evidence was one of the hallmarks of the scientific revolution, and Kepler's approach to the relationship between science and religion was an important part of this intellectual transformation. In many ways, Kepler's religious beliefs were a source of inspiration and motivation for his scientific work. His view of the universe as a reflection of divine harmony and order drove his desire to understand the cosmos in mathematical and empirical terms. At the same time, his scientific discoveries challenged traditional religious ideas and paved the way for a new way of thinking about the relationship between science and religion. Kepler's ability to reconcile his faith with his scientific work was one of the defining features of his career and a key factor in his lasting influence on both the scientific and religious communities. Johannes Kepler's relationship with religion and spirituality was central to his scientific worldview. His belief in a rational, mathematical order to the universe, which reflected the divine will, motivated his scientific inquiries and influenced his discoveries. Kepler's work exemplified the idea that science and religion could coexist, and his conviction that the natural world could be understood through mathematics and empirical observation was a key feature of the scientific revolution. While Kepler's religious beliefs shaped his view of the cosmos, his scientific discoveries challenged traditional religious ideas and contributed to the development of a new, more empirical approach to understanding the natural world. Kepler's ability to harmonize his faith with his scientific work marked him as a key figure in the intellectual transformation of the early modern period. Johannes Kepler's scientific contributions left an indelible mark on the development of modern science, particularly in the fields of astronomy, physics, and mathematics. His work not only transformed our understanding of the cosmos, but also played a pivotal role in shaping the intellectual landscape of the 17th century and beyond. While Kepler did not live to see the full impact of his discoveries, his legacy has endured through subsequent generations of scientists and thinkers who built upon his foundations. This chapter explores Kepler's enduring influence on the evolution of scientific thought, examining how his discoveries shaped future scientific paradigms, contributed to the development of new methodologies, and inspired intellectual movements that continue to define the trajectory of scientific inquiry today. Kepler's most immediate legacy is undoubtedly his 3 laws of planetary motion, which provided a clear, empirical description of how planets moved around the sun. These laws were revolutionary not only because they replaced the geocentric Ptolemaic model, but also because they demonstrated that celestial bodies followed precise mathematical relationships rather than the arbitrary, circular orbits of earlier models. Kepler's laws, particularly the second law, which posits that planets sweep out equal areas in equal times, and the third law, which relates the period of a planet's orbit to its distance from the sun, provided the first quantitative and predictive model of planetary motion. This marked a shift from a purely observational approach to a more analytical and theoretical one, making it possible for scientists to make accurate predictions about the positions of planets and other celestial bodies. Kepler's laws of planetary motion laid the groundwork for the later development of Newtonian physics. Isaac Newton, who admired Kepler's work, built upon Kepler's laws in his formulation of the law of universal gravitation and the 3 laws of motion. Newton was able to explain Kepler's laws through the concept of gravitational force, demonstrating that the same force responsible for objects falling to the ground on Earth also governed the motion of the planets. In this way, Kepler's laws became a vital part of the Newtonian framework that would dominate physics for centuries. The connection between Kepler's work and Newton's theories illustrates how Kepler's insights were not only groundbreaking in their own time, but also served as a stepping stone for the later scientific revolution. Beyond his contributions to astronomy, Kepler's legacy also extends to the field of mathematics. Kepler was a master of mathematical reasoning and was among the first to apply sophisticated mathematical techniques to describe physical phenomena. His use of geometry, particularly in his work on the elliptical orbits of planets, was revolutionary. Kepler's ability to describe the motions of celestial bodies through mathematical laws was a direct precursor to the later development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz. Kepler's insistence on the importance of mathematics in understanding the natural world helped to establish the central role of mathematics in modern science. Today, mathematics is regarded as the language of science, and Kepler's pioneering work in this regard set the stage for the development of mathematical physics. Another aspect of Kepler's legacy lies in his commitment to empirical observation and the use of data to support scientific theories. Kepler's work was grounded in meticulous observation, particularly in his analysis of the astronomical data provided by Tycho Brahe. Kepler's ability to extract meaningful mathematical relationships from Brahe's detailed observations marked a significant shift away from speculative and philosophical explanations of the natural world toward a more empirical, data-driven approach. Kepler's emphasis on observation and measurement helped to establish the importance of empirical evidence in scientific inquiry. This shift toward empiricism would later be central to the development of the scientific method, as championed by figures such as Galileo Galilei and Francis Bacon. Kepler's emphasis on observation and empirical data also played a crucial role in the development of experimental science. While Kepler himself did not conduct laboratory experiments in the modern sense, his careful and systematic observations of celestial phenomena set an example for future scientists who would rely on controlled experiments to test hypotheses. Kepler's insistence on the accuracy of measurements and his use of empirical data to support his theories helped to establish the principle that scientific knowledge must be based on reproducible, verifiable observations. This principle would become a cornerstone of the scientific method and would shape the development of modern experimental science. Kepler's influence extended beyond the realm of physical science and astronomy. His work also had a profound impact on philosophy, particularly in the area of epistemology, which is the study of knowledge and how we come to understand the world. Kepler's insistence on the importance of observation, measurement, and mathematical reasoning in the pursuit of knowledge helped to establish a new way of thinking about the acquisition of knowledge. In his view, knowledge about the natural world could only be obtained through careful, empirical observation and logical reasoning. This view challenged the prevailing Aristotelian philosophy, which emphasized deductive reasoning based on established principles and laid the groundwork for the development of modern scientific philosophy. Kepler's legacy also contributed to the gradual shift from a teleological view of the universe to a more mechanistic, cause and effect understanding of natural processes. In the medieval period, the cosmos was often viewed through the lens of divine purpose or order, with celestial phenomena interpreted as expressions of divine will. Kepler's work, however, demonstrated that the motion of the planets could be described through mathematical laws, independent of religious or metaphysical explanations. Kepler's willingness to adopt a more mechanistic view of the universe paved the way for later scientists, such as Newton, who would further develop the idea of a universe governed by physical laws, governed by cause and effect relationships rather than divine purpose. In addition to his intellectual contributions, Kepler's legacy was also shaped by the broader cultural context in which he worked. Kepler's time was one of intellectual ferment, marked by the rise of the scientific revolution and the decline of medieval scholasticism. Kepler, along with contemporaries such as Galileo and Copernicus, played a central role in the intellectual upheaval that challenged traditional views of the cosmos. The acceptance of the heliocentric model, championed by Copernicus, and the development of Kepler's laws of planetary motion were key milestones in the shift from a geocentric to a heliocentric view of the universe. This paradigm shift had profound implications not only for science, but also for religion, philosophy, and society at large. Kepler's legacy, in this sense, is inseparable from the broader transformation of European thought that characterized the scientific revolution. Kepler's legacy is also reflected in his influence on the development of modern astronomy. Kepler's laws of planetary motion were a critical step in the development of celestial mechanics, the study of the motion of celestial bodies under the influence of gravitational forces. The understanding of planetary motion and the ability to predict the positions of planets became essential for the advancement of astronomy, particularly in the study of the solar system and the exploration of space. Today, Kepler's laws are still used in astronomy to predict the orbits of planets, moons, and artificial satellites. The continued relevance of Kepler's work in modern astronomy speaks to the enduring impact of his contributions. Kepler's influence also extends to modern physics, particularly in the field of orbital mechanics. The mathematical principles that Kepler developed to describe the motion of planets have been applied to the study of artificial satellites, space travel, and interplanetary exploration. Kepler's laws of planetary motion have provided the foundation for the design of spacecraft trajectories, the calculation of satellite orbits, and the study of the motion of comets and asteroids. The Kepler Space Telescope, launched by NASA in 2009, is another testament to the enduring relevance of Kepler's work. The mission, which aimed to discover Earth-like exoplanets, is named in honor of Kepler's pioneering contributions to the study of planetary motion. Johannes Kepler's legacy has had a profound and lasting impact on the development of scientific thought. His work not only transformed our understanding of the cosmos, but also laid the foundations for the development of modern physics, astronomy, and mathematics. Kepler's emphasis on empirical observation, mathematical reasoning, and the search for universal laws helped to establish the core principles of the scientific method and marked a turning point in the history of science. Kepler's influence extended beyond the fields of astronomy and physics, shaping the development of modern philosophy, epistemology, and the mechanistic worldview. Today, Kepler's work continues to be central to our understanding of the universe, and his legacy remains an integral part of the intellectual history of the scientific revolution. Johannes Kepler's work was revolutionary for his time, and its impact reverberates throughout modern science, technology, and even culture. The 21st century has seen remarkable advances in fields such as space exploration, physics, and computational science, yet the foundational ideas laid by Kepler continue to be integral to our understanding of the universe. While Kepler himself could not have anticipated the technological advancements that have since taken place, his vision and discoveries provided the necessary groundwork for the scientific community to make these breakthroughs. This chapter explores the enduring relevance of Kepler's ideas and how his work continues to shape the scientific and technological landscapes of the present day. One of the most direct ways in which Kepler's work remains relevant today is through the field of astronomy. His 3 laws of planetary motion, which describe the elliptical orbits of planets and their motion relative to the Sun, continue to be fundamental in understanding the behavior of objects within our solar system. These laws have been essential for space missions, satellite placement, and the study of celestial mechanics. Kepler's laws also played a crucial role in determining the trajectories of interplanetary probes, such as NASA's Voyager missions, and the precise calculation of orbits for space telescopes like the Hubble Space Telescope. Without Kepler's work, the ability to send spacecraft to distant planets or even explore the far reaches of the solar system would not be possible. The Kepler Space Telescope, launched in 2009 by NASA, is a fitting tribute to Kepler's legacy. Its mission was to detect exoplanets, planets that orbit stars outside our solar system. Using Kepler's laws, the telescope was able to pinpoint planets with a size and orbit similar to Earth, some of which may even possess conditions suitable for life. The Kepler Space Telescope has contributed to the discovery of thousands of exoplanets, greatly expanding our understanding of the potential for life elsewhere in the universe. This ongoing exploration is a direct continuation of Kepler's vision of understanding the movements of celestial bodies, and his work remains a cornerstone for these new discoveries in modern astronomy. Kepler's laws are also critical for the study of gravitational forces, a concept which would later be fully developed by Isaac Newton. Newton's laws of motion and universal gravitation extended Kepler's work, providing a more complete understanding of how celestial bodies interact with one another. The connection between Kepler's empirical laws and Newton's theoretical framework created a powerful model that not only explains planetary motion, but also governs the movements of satellites, comets, and even black holes. The universality of Kepler's laws has made them indispensable in modern physics, where they continue to guide astrophysicists in their exploration of the universe. The intersection of Kepler's work with modern technology extends beyond space exploration. In the development of global navigation systems, such as GPS, Kepler's principles of orbital mechanics play a vital role in ensuring the accuracy of satellite systems. GPS technology relies on the precise synchronization of satellite orbits and the understanding of how celestial bodies move in relation to one another. Kepler's laws provide the foundational understanding that allows engineers and scientists to account for variables such as the curvature of the Earth, the speed of satellites, and gravitational influences in order to deliver accurate positioning data. In this sense, Kepler's work is embedded in the very infrastructure that modern society depends on for navigation. Kepler's influence also persists in the study of planetary systems and the search for habitable worlds. As astronomers continue to investigate exoplanets and their potential for supporting life, they often use Kepler's laws to determine the likelihood that these planets exist in a habitable zone, the region around a star where liquid water could exist. Kepler's work has enabled the establishment of criteria for habitability that continue to guide the search for life beyond Earth. The idea that the laws governing our solar system could be applied to distant star systems has expanded our understanding of the universe and inspired the quest for other Earth-like planets. Kepler's legacy extends beyond the realm of physical sciences into the world of philosophy and the history of ideas. His work helped usher in a new way of thinking about the relationship between humans and the universe. By replacing the geocentric model with a heliocentric one, Kepler shifted humanity's view of itself from the center of the universe to one small part of a vast, interconnected cosmos. This change in perspective laid the foundation for the scientific revolution, which ultimately transformed how we think about knowledge, observation, and the nature of reality. Kepler's insistence on using observation, measurement, and mathematics to understand the natural world helped to establish the empirical methods that define scientific inquiry today. Kepler's philosophical approach to science was also grounded in his belief in a rational, mathematically structured universe. This conviction that the universe operates according to consistent, discoverable principles continues to resonate in contemporary science. Today's physicists, astronomers, and mathematicians continue to search for the underlying equations that govern the cosmos, whether it be in the search for a theory of everything or in the ongoing quest to understand quantum mechanics. Kepler's work helped demonstrate that the universe is not governed by capricious forces, but is instead structured in a predictable, comprehensible way. This worldview is a key element of modern scientific thought, one that continues to drive research into the fundamental nature of the universe. Moreover, Kepler's exploration of the concept of cosmic harmony, his belief that the movements of the planets could be described in terms of mathematical ratios and proportions, has had a lasting impact on the intersection of science and the arts. His notion that the cosmos is not just a mechanical system, but also a harmonic one resonates with both musicians and artists, inspiring them to seek patterns and beauty in the natural world. Kepler's work has influenced fields ranging from music theory to architectural design, with a search for harmonious proportions and relationships between form and function mirrors his understanding of the cosmos. His belief in the mathematical beauty of the universe remains a powerful idea, one that transcends disciplines and continues to inspire creativity in diverse fields. In the realm of education, Kepler's impact on scientific methodology cannot be overstated. He was one of the first to demonstrate the power of applying mathematical reasoning to physical phenomena, setting a precedent for modern scientific inquiry. The practice of deriving mathematical equations from observational data is a central method used in contemporary scientific research. Students in physics, astronomy, and engineering today continue to study Kepler's work to learn how the rigorous application of mathematics to empirical observation can lead to significant breakthroughs. His work also plays a key role in helping students understand the evolution of scientific ideas, particularly in relation to the transition from ancient Aristotelian physics to modern Newtonian mechanics. Kepler's ideas have also influenced the development of modern cosmology, the study of the universe as a whole. His laws of planetary motion are a fundamental part of our understanding of how galaxies, star systems, and black holes operate. In modern cosmology, Scientists use Kepler's equations as a basis for modeling the movement of celestial bodies on a galactic scale. Understanding the movement of individual stars within galaxies, the dynamics of star clusters, and the motion of galaxies themselves is still reliant on the same mathematical principles that Kepler first outlined. In this way, Kepler's laws continue to be integral to some of the most ambitious areas of scientific inquiry. Finally, Kepler's contributions have inspired countless individuals to pursue careers in science and exploration. His persistence in the face of adversity, his devotion to the pursuit of truth, and his groundbreaking work have made him a model for generations of scientists. The Kepler Space Telescope itself is a fitting tribute to his lasting legacy, symbolizing the continued pursuit of knowledge that Kepler so passionately embodied. His influence extends beyond the field of science, serving as a reminder that the quest for understanding, no matter how difficult or uncertain, can lead to profound insights about the universe and our place within it. In conclusion, the enduring relevance of Johannes Kepler in the 21st century cannot be overstated. From space exploration and gravitational physics to philosophy and music theory, Kepler's ideas continue to shape the way we understand the cosmos and our place in it. His work was a cornerstone of the scientific revolution and laid the foundations for many of the discoveries that have followed. As we continue to explore the mysteries of the universe, Kepler's legacy will remain a guiding force, a testament to the power of human curiosity, reason, and the unrelenting pursuit of knowledge.